Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. When toluene reacts with chlorine, Cl2, the reaction conditions determine where chlorination occurs. In the presence of light, HV, the reaction proceeds via a free radical mechanism. In the presence of a Lewis acid catalyst, example, UlCl3 or FeCl3, the reaction proceeds via electrophilic aromatic substitution, EAS, substituting on the ring. Moving on to the next step. Identify the reaction conditions. The question specifies in the presence of light, which means photochemical free radical conditions, HV. Moving on to the next step. Free radical chlorination under light. Light, HV, causes homolytic cleavage of Cl2 to generate chlorine radicals, Cl. These radicals preferentially attack the benzylic position, the methyl group side chain, rather than the aromatic ring, because the benzylic radical intermediate is stabilized by resonance with the aromatic ring. And for the final step, the benzylic CH bond of the CH3 group is weaker and more reactive toward radical abstraction. The chlorine radical abstracts a hydrogen from CH3 to give a benzyl radical, C6H5CH2, which then reacts with Cl2 to give benzyl chloride, C6H5CH2Cl, and another Cl to continue the chain. Product identification. The product is benzyl chloride, PHCH2Cl, which is option C, a benzene ring with a CH2Cl group attached. Why other options fail? Option A, polychlorination of the ring at multiple positions would require ES conditions, not free radical light conditions. Also, adding Cl to ring carbons directly in this pattern is not what light promotes. Option B, orthochlorotoluene is an EAS ring substitution product favored with Lewis acid catalyst, not with light. Option D, parachlorotoluene is also an EAS ring substitution product favored with Lewis acid catalyst, not with light. Therefore, the correct answer is C. Therefore, the correct answer is option C.